I'm going to mute myself.
Are we live?
We are. Please go ahead.
All right. So hi, everyone. Welcome to our quantum matter seminars, who today receives Professor Kieron Burke from UC Irvine, who is going to talk about DFT and machine learning, this new business that is very, very promising. And he's going to share with us these amazing results that he has been working it over the past years, right? Thank you very much, Kieron, for being with us today, for accepting your invitation, and the stage is yours.
Thank you, Christia and Adrian, and thanks everybody for inviting me to give this talk. It's actually, the talk will be focused on mostly fundamental things, and it will cover quite a lot of ground, and I hope there'll be something of interest to everybody here. Okay, so and I'll talk about a few different kinds of work that I've been involved in, which focused entirely on strongly correlated systems. Let's see. Okay, so there'll be a sort of central theme, right? So looking at what people do in this seminar series, right? It's strongly correlated materials. My focus tends to be on finding really quite accurate energetics for such materials, ground state energies mostly. I will just go through some myths about density functional theory, and then end with some progress toward functionals using machine learning. Okay, so, and there's sort of 4 parts, DFT in 5 minutes, then the Hubbard, the 2-site Hubbard model, using it to understand how DFT works. Then work done mostly with Steve White and Miles Studenmeyer and other people doing electronic structure in 1 dimension using DMRG, and then finally the machine learning for strongly correlated functionals. So yeah, and please feel free to interrupt me anytime. So DFT in general, right? So one thing I want to emphasize here is molecules are easier. So I sit in a chemistry department, and a lot of work we do is molecular, and it's just easier to study them because it's easier to do highly accurate calculations with molecules. And so we have lots of quantum chemical methods of getting very accurate numbers for small molecules, and we can use them to validate or train our density functionals and get basically higher accuracy than you can usually get with materials calculations. I'll use the term first principles instead of ab initio, because in quantum chemistry, ab initio is usually reserved for wave function-based methods, not DFT. And we'll see that the main job of DFT is to simply extract total energies. So the electronic structure problem, we'll do non-relativistic, like the Born-Oppenheimer approximation. We'll avoid magnetic fields, and I'll not bother writing out spins. So you have this general problem of a Hamiltonian, which is always the same in form for all these different electronic systems. The kinetic energy of the electrons, the electron-electron repulsion, which is what makes it a difficult many-body problem, and then the one-body potential, which is the only thing that varies from one system to another. And we have the variational, the Schrodinger equation, or for the ground state energy, the variational principle. Now, DFT does this sleight of hand, where one way to think about it is simply rewrite the variational principle in 2 steps, minimize overall wave functions that are allowed, yielding a certain density, and then minimize over densities. And when you do that, you discover, as Holmberg and Cohn first did, that there's a variational principle based on the density alone, but it involves using this difficult to calculate f of n. And the real value of DFT is these Cohn-Sham equations, where you imagine a fictitious set of non-interacting electrons with the same exact density as your system. And when you do that, you can show that there's a little piece of the energy that you don't know the exchange correlation energy in terms of these cone-sham orbitals. And if you can differentiate that with respect to the density, you get a closed self-consistent set of orbital equations. And for any doubting Thomases that might still be out there, this is the simplest system. You can think of a helium atom. This is the exact ground state density. This is the true Coulomb attraction to the nuclei, and this is the exact cone-sham potential for that system. And if you put two non-interacting electrons into this cone-sham potential, you get exactly that density. You just doubly occupy the 1s orbital. And if you know that, you can actually deduce the exact ground state energy in this case. So all the DFT calculations pretty much in the world today are doing approximate cone-sham calculations. They approximate that potential, and most importantly, they approximate that energy. So this was a breakthrough at the time. Holmberg and cone-sham, a theorem, a computational recipe, and a very simple approximation, the local density approximation. These days, since the early 90s, we have more sophisticated approximations, and actually these ones are now not the most latest that people are using. The local density approximation just uses the density at a point. The generalized gradient approximation uses the gradient, and a global hybrid mixes some fraction of Hartree-Fock. Okay, and applications. So in chemistry, for example, new catalysts for the Haber-Bosch process were found about 10 or 15 years ago. The materials genome project in material science is almost all DFT calculations. The latest room temperature superconductors under pressure were predicted in DFT searches based on Neil Ashcroft's ideas, and then found experimentally. People understand Jupiter's interior using this Juno probe that goes around every 57 days, and they use warm dense matter finite temperature DFT calculations to understand the equation of state of the interior. The chips needed for the airbook were half the size of the previous ones, and DFT was used in the materials design to make them lead-free. Turns out there's you can do DFT calculations of fish and get them published in the Journal of Physiology. And even you can figure out which water to make your coffee with using DFT calculations. Okay, so this is now a huge enterprise, about 50,000 papers a year, published each year doing DFT. Now, but we want to get at, so that's great, and there are lots and lots of successes, or people wouldn't be using it. But what we're interested in is basically failures, especially for strongly correlated systems. So I use the Hubbard dimer as an example to sort of reinforce some basic ideas about DFT. And I like to tell the story how I ran into this kind of weird Scottish guy. Actually, I knew him quite well at a meeting a few years ago, and we used I used the Hubbard dimer to explain to him the cone-sham idea. And after about an hour of arguing, he thanked me profusely and said that was the first time he really understood what this cone-sham scheme really meant. And about a year later, he was awarded a Nobel Prize in physics. So that was Duncan Haldane. I just like to point out that he didn't get a Nobel Prize in physics until after he understood what cone-sham DFT is. Okay, and we're going to see that there are a lot of myths about DFT, some sort of propagated by people sort of using it, some people doing many-body theory, some people by the DFT people themselves. So they're not really lies, but sort of confusions, I'd say. So I just finished this article for a very nice school that has run out of Jülich each year, and that title, Lies My Teacher Told Me. But it's based on these review articles, and I won't go through to mention other people's work. A lot of the references are in these kinds of articles. Okay, so so we just take an asymmetric two-site Hubbard model. So we have a U charging energy, but we have two different sites, and we have a potential difference between them. And when U is much bigger than the potential difference, it'll be a strongly correlated system. And when U is comparable to delta V or smaller, it'll be weakly correlated and in this sort of charge transfer regime. And you can analytically write down the formulas for the energies and everything you might want to know by hand. And if you sort of plot out a sort of phase diagram, here, this should be uppercase U. I use units where 2t is equal to 1. This is U, and this is delta V divided by U. So you have this Mott-Hubbard regime, this weakly correlated regime. And this dividing line is where something like 86% of the wave function of the Kohn-Cham wave function, the exact Kohn-Cham wave function, has 86% overlap with the true wave function. Okay, so the first Holmberg-Kohn theorem is simply that there's a one-to-one correspondence between densities and potentials. So in this little model, so normally doing quantum mechanics, you think, well, I give you the potential and I calculate quantum properties like delta n. But I can plot this on the right here on its side, and I see that for any given value of U, there's a monotonic function relating delta V to delta n. And that's the essence of the first part of the Holmberg-Kohn theorem. There's only one ground state delta n that goes with any delta V. The second part, using that constrained search, is to pull out this part of the functional, and we can easily do that. And here I've plotted as a function of n1, the occupation on one of the sites. And we see that you can plot this very nice functional, which contains lots of information about the system for each different value of U, right? For a given U, you're interested in that. And that part is universal in the sense that it doesn't depend on delta V explicitly. And so what you do is you apply that variational principle, you get an Euler equation, and that's actually going to determine your density, and you can then feed it back in and get the energy. So you can do that explicitly in this model. And you can do the Kohn-Cham equations. So you find a tight binding delta Vs, which gives you the exact same ground state density as your original system. So you write the big F in terms of kinetic energy, the Hartree energy, and the unknown exchange correlation piece. And then you get this Kohn-Cham potential in terms of its derivative. Now, what's interesting is what happens when we turn up U, where it's generally thought that lots of DFT methods fail. So when U is very small here, we have U as 0.4. Now we plot as a function of N1, the occupation on one site, that's the density. And you see here is delta V, the potential that goes with each value of N1. So U equals 0.4 is only barely interacting. And we see that the Kohn-Cham potential is not much different from the original potential of the interacting system. And then this red line has got both the Hartree and the exchange pieces, and the green line has correlation as well. And you can see that the green and the red are almost the same. There's very little correlation. If you ignore it, you'll get a very good approximate answer, and that's Hartree-Fock. When we turn up U, we begin to see more of a difference with correlation, but it's still small compared to exchange and the Hartree effects. And the shape of these two is very similar. But when we turn U up to a very high value, you can see that the correlation now dominates over Hartree and exchange. And what is it doing? Well, we have to always think of the logical definition. The Kohn-Cham potential is defined to reproduce the ground state density. So when U is very large, unless N1 is very close to 0 or to 2, very asymmetric, the Kohn-Cham potential must be very close to zero because we'll push it toward the center. But the interacting potential is this black line, and so you see the correlation does a lot of work to essentially oppose the interacting potential to make it a non-interacting system which has the n1 close to 1, even though the interaction is very strong. So this means that correlation effects become very big when U is large. Okay, but the important point here is this way of thinking about the problem, which is that it's defined to reproduce the exact density. So you can have a lot of intuition about Hartree and exchange and correlation, almost all of which will fail when the correlation starts becoming too big. But the logic will still work. Okay, now the purpose of this ground state DFT machinery is essentially, if you look at it, to find pretty accurate energetics, ground state energies as a function of the nuclear coordinates. This tells us a huge amount of information, and especially in chemistry, we want to know all sorts of energies. The positions of atoms, the lattice structure, and so forth can all be predicted once you're able to do that, and that's what it's doing. And actually, the most recent estimates say that about a third of NSERC supercomputers here in the US are now actually devoted to DFT calculations, so more than climate change and any other single topic. Okay, so now let's get to some meat for strong correlation. So the gap is always an issue. I'm talking about the fundamental or charge gap, the gap you measure by putting on electrodes. And so in our little two-site system, we can actually calculate what's going to become the gap. You can get the gap by doing a sequence of ground state calculations, and therefore it should work if you have the exact functional. So the gap is the difference between the ionization energy and the electron affinity. And for a sort of regular semiconductor or insulator, as you go to the thermodynamic limit, that will give you the usual definition of the gap. There's an exact theorem that tells you that the cone-sham HOMO is minus I. You can prove that for the exact cone-sham system. And what you find is that the gap of the cone-sham system, which is what comes out of a periodic calculation, does not match the true gap because there's a difference between the electron affinity and the LUMO, the lowest unoccupied molecular orbital, which is the valence band minimum. And when U is moderate, as here where it's 1, we see that there's a small underestimate of the gap. But when U is very large, you see that there's a large underestimate of the gap. And what all this is saying is that if I do an exact cone-sham calculation with the exact functional, I'm not supposed to get the gap right. That isn't what ground state DFT does. I'm not supposed to be able to read off the gap from the cone-sham band structure. And even further, we can look at the spectral function, the exact many-body Green's function, the one-body Green's function for the interacting system, and compare it with the exact cone-sham Green's function, and they don't match. But when U is small, they look roughly similar. The quasi-particle peaks are in about the right place and with about the right height, but the satellites aren't there. But when U gets much larger, we see that there's a big underestimate and there are bigger satellites which are missed entirely by the cone-sham, the exact cone-sham. So we have to think about what does this mean, right? When a system is strongly correlated, the cone-sham spectral function is not close to the physical Green's function. But all the exchange correlation functionals that people use are trying to just create the accurate energy differences. So when we say that DFT fails, when we're talking about strong correlation, usually that isn't really quite right. What we're saying is that this naive interpretation of the cone-sham eigenvalues as some sort of excitations is not true. They're not even close. And that's correct, but it isn't a failure of DFT. Even with the exact functional, as I just showed you, you get that big difference. And then you have to turn to many-body methods, essentially, at the moment, in order to, if you want to find those quantities as well. So cone-sham DFT is not mean field theory, right? I can give you the exact functional, and it will do as I just showed you, and it won't do many of the things you would like it to do. So these we have a way for optical excitations using time-dependent DFT to correct cone-sham transitions. Okay, and so this interpretation, so people who are doing more sophisticated methods, like, well, DFT plus U is a little bit outside of DFT. Dynamical mean field theory is a more sophisticated thing, but it's outside the realm of sort of rigorous DFT. It can be an excellent approach for getting, say, moderately strong fluctuations, but what you're doing is you're adding many-body theory on top of a sort of DFT starting point. And, you know, people talk about, well, what's the most effective starting point, or what's the double counting correction and so forth. But the problem is that, you know, even if I give you the exact functional, right, it won't be, you know, the downfolded Hamiltonian. It won't be the most effective mean field theory. It is simply that Hamiltonian whose single particle ground state matches that of the interacting system. Nothing more or less than that. Okay. Where are we? Okay, so now we're going to go on to the next section. That was my time. Good. Are there any questions so far on this part? I said a lot of stuff pretty fast. I guess I look at the chat as well. Okay. Chris here will bug me if there's questions. Okay, I'll keep going. So I can use little models, lattice models like the Hubbard, to explore these aspects of exact DFT, but they are not good for looking at approximations in DFT because they are not real space Hamiltonians. And it turns out that the success of DFT is totally tied to the success of the approximations is totally hardwired to real space Hamiltonians. And that's why the local density approximation is the starting point of all DFT approximations. So what we're going to do next is go reintroduce the real space. So electronic structure, oh, I'm going the wrong way, in 1D. So it's much easier and faster to do calculations in 1D than in 3D. And what's nice is DMRG gives you essentially the exact solution. So what we do is so this is all work with Steve White. We started about 8 or 9 years ago. We use a grid of about 20 points per sort of one-dimensional atom. So we can do about 100 atoms because you can do DMRG on say a 1D lattice of about 2,000 lattice points. And we use an exponential to mimic the Coulomb repulsion of 3 dimensions because it's too singular in 1 dimension. And we can also, we extracted the uniform gas numbers from DMRG as inputs to the local density approximation. Okay, going the wrong way. So one generic failure, which is part of it, the failure of DFT for stronger correlation, is that as you break a bond, things do not dissociate to the right limit. So this is this is a generic problem of mean field type theories that are based on a single Slater determinant as a reference, and it's been known since the 30s in quantum chemistry within Hartree-Fock. You pull a bond apart, and your single reference theory is not a good approximation for the separated atoms. And this is one part of sort of strong correlation. A second part is, as the system size grows, that the broken symmetry solutions, when you stretch the bond in the approximate theory, have even get more and more. There are more and more of them. Okay, so this is a very sort of standard prototype picture when you try. So this is from our 1D electronic structure world, where and the curves mimic almost exactly those in 3 dimensions. And what's going on here is the black line is the DMRG energy for this H2, and it's dissociating to 2 separate one-dimensional hydrogen atoms. And if you do, say, restricted Hartree-Fock or restricted LDA, what happens is, so you're restricted to be in a spin singlet, then it doesn't associate to the right limit. On the other hand, if you allow it to break spin symmetry, it does, and here we go, and it goes to essentially the right value in the Hartree-Fock case for 1-electron systems when they're separated. But there's these Coulson-Fisher points where it breaks symmetry. So this is very unsatisfactory, and basically your functional, your semi-local functionals do very badly once you get to that point. Okay, and you can see here that if you allow that symmetry breaking, that here the LDA approximation for the difference between the atoms and the molecule, which is the binding energy, is very, very good, which is also true, well, for GGA in 3 dimensions. Okay, so what did we do with to study strong correlation in DFT? So this is the normal Kohn-Sham algorithm where you solve the Kohn-Sham equations iteratively. So what could go wrong when you have a strongly correlated system? The theorems prove that the Kohn-Sham potential is unique. So it's not like you're going to find more than one for one system. So that's okay. Whether or not it exists, people cannot prove in general that the Kohn-Sham potential exists. But we always found that it did. We never ran into a case where we couldn't find it. But convergence turns out to be a big issue. If you cannot converge the Kohn-Sham equations, what if you never find the Kohn-Sham potential? And in fact, many people had found this in these stretched systems, that it becomes harder and harder to converge. So anyway, so what we did was we set up the DMRG to do what's called an interacting inversion, which is an insanely expensive thing to do, where you give me a random density and I find the interacting system for which it's a ground state. And so we go through this cycle in purple, which is like ridiculous, more expensive than solving the Schrodinger equation. And then we attached it to these Kohn-Sham equations. We were able to do the first ever Kohn-Sham calculation with the exact functional being iterated inside. And in fact, it turned out we could prove that it always converges with a little, once we made certain simplifying assumptions, you could guarantee that it always converges. Okay. I'll just mention this briefly in case anybody's interested. This is something we created about a year ago, conditional probability DFT. It's an alternative way of getting at strong correlation. And here's the H2 dissociation curves in 3 dimension in this case. And we get a pretty good curve from this conditional probability theory, but I'm not going to talk about it here. Okay, because what I want to get to is finding the functional with machine learning that a lot of people are interested in. Now we had done a lot of earlier work. And so this is work of a very good graduate student I had, Lee. And this, sorry about the resolution here, but we had done a lot of work to show that we could take these hydrogen atom chains and we train on chains of finite length, and we take a lot of training data and we use it to create a density functional, which we could then show gave you, this is in a slightly weakly correlated case, but showing you that the machine learned functional with enough training data would converge to the thermodynamic limit of the infinite hydrogen chain to within chemical accuracy, which is about 1.5 millihartries, so that we could actually learn well enough using a lot of tricks that we invented from using them from the machine learning world. We could learn it well enough to get this kind of accuracy. So this showed that with the fairly simple machine learning algorithms and a lot of data, we could actually create a functional. We could find a functional which works for strong correlation and in the thermodynamic limit. But it did take a lot of data. But more recently, so lots of people since those days have gotten into the game of finding functionals using machine learning. And there's lots of interesting work going on. A lot of it is a bit different from what we tend to do. A lot of it involves trying to make standard approximations better. And that, is very important to make it more accurate, but it won't help solve strong correlation problems. And then lots of it also involves finding potentials in cone-sham problems rather than, let's say, energies or densities. But as I've focused on, right, there's the supreme importance of the energy. In reality, most DFT calculations are designed to give you good energies, not potentials and not densities. And most errors in DFT calculations are dominated by the error in the energy. And the map between densities and potentials is actually notoriously tricky. And so when you're trying to learn a cone-sham potential, you're trying to learn something harder than you might need to learn. It is much better to learn directly the density itself. So why the density? It gives you all possible derivatives of the energy with respect to the one-body potential. It contains the forces, which are also, of course, of great interest. And it bypasses all the difficulties of relating the density and the potential. But from a formal point of view, it always looks like it would be a good idea to study the potential. So the work I want to sort of focus on and end up with, I guess, came out earlier this year. So this very good graduate student, he went off to Google Accelerated Science, and we worked together under the team, I think, created by Patrick Riley at Mountain View, and then an excellent new physics graduate student, Ryan Pederson, and myself worked with these guys. And so this came out just earlier this year. And so it's about using sort of some of the latest techniques in the machine learning world to produce functionals for strongly correlated systems with very little training. So, and Lee's great idea was using the cone-sham equations themselves as a regularizer. So previously we had used kernel ridge regression, which works very well for small amounts of data. But here, and in the last 10 years, neural networks have become much more popular. So neural networks are very good with large amounts of data, but smaller amounts of data, they often need substantial regularization, ways of avoiding overfitting the data that they have. And in this case, we'll see overfitting is really important to avoid. So the idea was, could we learn a functional for breaking a bond or say working for a strongly correlated material with very little data. And a very good graduate student from Tokyo, Ryo Nagai, with his group had come up with the idea of using the density in order to learn the functional, and show that you could learn more with using the density. So this is taken from this paper. So so we use the DMRG to create lots and lots of training data, but it turns out we don't need very much of it. We actually use most of it for testing by the end. So you take one of these 1D H2 binding curves. So this black dashed line here is that binding curve, the accurate one. And in these 4 panels, what we're seeing is different levels of models, of machine learning models, trying to reproduce this curve. The direct ML, don't worry, that's trying to learn the energy just directly like a force field. But here we do a local density approximation and a GGA, more sophisticated one. And in each case, we see that we end up with a curve that does that bad thing where it doesn't go to the right dissociation limit. So this thing called KSR Global is a neural network, which instead of just using the density in the region of where you are to estimate the energy, it uses the density everywhere in the system. So it's able to look at the density, and using the tricks that we developed, we were able to figure out the very accurate, within chemical accuracy, binding energy curve with just 2 points, knowing the energy and the density at those 2 points and 1 validation point here in the middle. So we take a point that's weakly correlated near the minimum, near equilibrium, and a point that's stretched, that's past that Coulson-Fisher point, but with just these 2 points, we are able to reproduce the entire curve. So how did he do that? Well, okay, so the scheme is sort of very clever. So it uses this differentiable programming that's becoming very popular as a way of getting sort of physics into machine learning. So what happens in the scheme is you are iterating the Kohn-Sham equations forward, but then you are looking at, and typically the last 15 Kohn-Sham iterations, and using all of them as part of your learning. And what happens is, as you can see, what's happening with each iteration is this was the first guess. And then when it uses this regularizer, so what it's doing is it's using it to not overfit the curve. We see that it sort of bounces around and starts getting closer and closer to the exact curve. Now, if you leave it going too long, it will actually go past the exact curve because it will overfit. So let's take a look and see. What happens is, if we look here, this is a representation of a 2-dimensional projection of the density in one of these problems at a distance of 3.8. And at first, this is what happens in the Kohn-Sham iterations. So this is where, the neural network is some configuration giving you some functional that's no good, and it iterates that one, and then it goes many, many times. And as it goes along, it's finding these trajectories which bring it closer and closer to a highly accurate, here's the exact density. Now, if you leave it running too long, you get to the exact density, but you have overfitted. This whole region here is all extremely close to the exact density. And in fact, the curve you want is this blue one, which is sort of halfway through the cycle, because that one gives you very close to the exact density, but also the very accurate energies. And I'm not going to go through it here, but we find that this one is the final one that's overfit. these are pictures of the densities in the different iterations. So each time it's doing a different, it updates the functional based on what happened in between, and then runs the cone-sham iterations again. But it's using how it learns the energy by iterating the cone-sham scheme. It's using that to not overfit, and the validation point, to not overfit the functional. And what's remarkable is that this generalizes extremely well. So with just 2 data points, we could get the H2 curve. With 2 data points, we could get a H4 curve, equally spaced H4, and then stretched. By putting in something called a self-interaction gate, we get H2 plus exactly right. And here's H2 molecules coming together. Now, they don't have the usual van der Waals interaction that you get in 3 dimensions, but you can see that this is without any training at all. Using the functional trained for H2 and for H4, we get a very accurate, not quite chemically accurate curve using this global functional. So let's see. These are learning curves, just again showing that it learns much faster when it has the density involved and not just the energy. And then again, this is a calculation done of H4 that's been stretched. And it's just showing that if we do our full KSR cone-sham regularizer, including both densities and energies to train, we get really good, even really good potentials at the end, whereas the densities and potentials are not good if you just train on the energies. So using the density was vital for making this thing work. And also having the differential programming so that we could back propagate the functional to go downhill to do our gradient descent. So future directions with this work is we're generalizing it to spin DFT. We test many different variations and flavors of this. We're going backwards in a sense and looking, does it work for weak correlation? People care about that. And in fact, there's a Phys Rev letter from a couple of weeks ago where people used it and it did work well for weak correlation, but that was again for approximate functionals, not the exact ones. And does it work for asymmetric cases? And all of it should work just as well for 3D. This is what I put on my slide originally, but those people, Vinko is one of the authors in this Phys Rev letter, are doing it in 3 dimensions. And the scheme works just fine. And we will go back and redo those calculations in 3 dimensions. So there's a review of that about, all the work on approximating density functionals available here. And let's finish up. So here are the things I've told you. So DFT is very successful, not so much at strong correlated systems. Sometimes sort of failures of DFT are people that report failures. It's not really a failure of DFT. It's a failure of this naive assumption about interpreting the cone-sham eigenvalues. You can see in explicit cases that the cone-sham spectral function is not close to the true function. The exact gap is not supposed to match the cone-sham gap, even with the exact functional. We prove that the cone-sham equations converge, and then we've seen that machine learning can produce fully non-local functionals, which capture strong correlation. So you can embed you can learn the exact functional using a neural network for at least simple cases, and it does work for strongly correlated systems. And thanks to DOE for funding, and thanks to you guys for your attention.
Thank you very much, Kieron. So now we have time for questions. Maybe I can start with that question. I was wondering if in the 1D case in which you inverted the
Yes.
Conshan equations to find the Conshan, if you compare it with that inversion scheme developed by Irene D'Amico, she had a nice work on that with Coe.
Yes. So there are maybe of the order of a dozen different inversion schemes that people have developed over the years, and it depends on if you're using plane waves or a grid or localized atomic orbitals, sort of which one might be best. We used a very simple, simple-minded brute force one, which is fine when you're on a grid and you don't care too much about the cost. And again, because we were working in one dimension, the computational costs are just so much lower that we essentially could waste computer power and not worry too much about it. And in particular, you have to do these inversions both for the interacting Schrodinger equation and the non-interacting one. And so, we would actually do precisely the same inversion. The interacting one is much, much more expensive. But in order to make the errors cancel exactly, we would just set the interaction to 0. We multiply it by 0 in the computer, waste exactly the same amount of computer power, but it would give us this sort of perfect cancellation of errors. So most of those inversion schemes are for the non-interacting system. And and all of them, or there are various improvements that people have made over the decades, it's a very tricky, sensitive problem doing these inversions, and getting the Conshan potential is actually much trickier than it looks at first. At first you'd say, well, non-interactive problem, how hard can it be? But actually it turns out to be much harder than we realized. To do it cleanly, let's say. And people are working on this all the time. And yes, Irene's scheme is a good one. Yeah.
Thank you. Now I have questions. Bernardo first. Bernardo, you're muted.
Oh, okay, thank you. Thank you, Krisha, because I couldn't unmute myself. So that was fantastic. Thank you, Kieron. I really I appreciate a lot. One thing I wanted to ask you, because as you say, in fact, we cannot describe the gap with density functional, but we have this very little modification of density functional that we call generalized density functional. And then we do the minimization with respect to the Conshan orbital instead of the density. And then Purdue demonstrated that actually if we have the exact functional, in that case, we can get the fundamental gap. So do you agree with that? Because this is actually very useful for us. The reason I'm mentioning that, we have a new generation of functional which is based on meta GGA, that we get gap incredible in ITC superconductor and things like that. So I wanted to ask your opinion on that.
Yes, well, I'm glad you asked me that. So I didn't include that part in the talk because I wasn't sure how much people knew about these kinds of things. So probably the paper you're referring to is this long paper with about 14 authors from about 4 years ago of John, so which looking at generalized Conshan for gaps. And I know that paper well because somewhere among the 14 authors is me, right? So let me explain exactly what happens. So, well, okay, there's a few different things. So one is you can get gaps from pure Conshan DFT by adding and subtracting electrons like I did in our little one-site case. And I seem to have skipped over it, but I have a picture, and it's in the first paper I did with Steve, showing this iconic example of a 1D hydrogen chain where the Mott-Hubbard gap that we calculate exactly in the DMRG is 10 electron volts, and the Kohn-Sham gap is exactly 0. So that's a demonstration beyond all doubt that you have this difference with pure Kohn-Sham. Modern functionals have hybrids or meta-GGAs, as Bernardo mentioned, have an orbital dependence. You can solve the equations not as Kohn-Sham equations, but as what are called generalized Kohn-Sham, where you treat the orbital dependence just like you would in Hartree-Fock or many-body theory. So you have an orbital dependent functional. That isn't the original pure Kohn-Sham theory, but it's the way people do the calculations with functionals like HSE06. And they do give you, that's a range separated hybrid, and it does give you moderately, it gives you pretty good gaps for moderate gap semiconductors up to 5 or 7 EV. And so HSE06 does give good gaps. Its Kohn-Sham gap would still be smaller than the gap that people are calculating, but because they do this generalized Kohn-Sham procedure, you can show that that actually gives you the equivalent of the charge gap. It's approximating the charge gap when you read it off the band structure from that calculation. The meta-GGAs have a weaker orbital dependence, and so they tend to give you something in between HSE06, which tends to be pretty accurate, and a PBE, which is not got an orbital dependence and approximates the Kohn-Sham gap rather than the true gap. So if your meta-GGAs, they should give you wider gaps than, say, PBE, but they shouldn't necessarily produce a very accurate gap. The effect is weaker than in a hybrid. But so the hybrids are mixing in many-body theory in that sense, and they're giving good gaps for moderate gap cases. But that is generalized Kohn-Sham, as you said, which depends on the orbital dependence. And it looks like they're working well for good reasons, but the meta-GGAs should widen the gap when they're done in a generalized Kohn-Sham, but shouldn't necessarily be that accurate. So I would always run, if you can afford it, run HSE06 as well. And then if the gap is way too big, then something may not be quite right. Yeah. But thanks for bringing that up. Yeah. So I decided not to comment on that. Okay.
So can I go ahead?
Yes.
Okay. Thanks. Kieron, was very, very nice talk and very interesting as well. My question is the following. For example, you mentioned that when you use energy, for example, to feed your neural network, for example, you get, I'd say, not so accurate result in terms of chemistry, let's say, let's put it this way. When you use, for example, instead of this, when you use density, then you get something better, right? That's what you said.
Yes.
My question here is the following. For example, do you think there is a very strong physical reason for that, or this is you are just improve your descriptor and you get lucky and this is
no. I think there. I mean, no, in the sense that I think there is a very strong physical reason, right? So one way to think about it is, as I've mentioned way back at the start, right? This breakthrough from the 60s was based on using the density as the basic variable, right? Now, that was all sort of, in a sense, intuitive, based on some formal arguments, but largely intuitive, and now we understand them much better. So there's a crucial part, which is that the actual systems that people care about, that people do all these calculations on, are all Coulomb interacting systems, not just Coulomb between the electrons, but Coulomb attraction to the nuclei. It's a very tiny infinitesimal fraction of all possible systems. But if I take two systems that people care about, right? If I sort of draw a line between any two potentials, saying, so I interpolate between them, I can always go a very small distance along that line, and the change in the energy will be given by the, an integral of the functional derivative with the density. So the density, when you use the density, it's telling you about the derivative of the energy in directions that lead toward other problems that you care about. So there's an infinite number of directions, most of which you do not care about, right? If I make an infinitesimal change way out in the tail of the tail of the system, it doesn't matter. If you study the potential, it tells you all those changes, right? But the density itself is sort of telling you about energy changes that you care about. And that's why I believe using the density is really fundamental. That's sort of one. So it isn't just an arbitrary descriptor. Another way to think about it is it's the density, classical electromagnetism. It's the solution of the Poisson equation, right, for the macroscopic properties of a material. But Poisson doesn't show up in the Schrodinger equation, right? It's not there anywhere. But once you use the density as a variable, then you have all the long and not so long range electrostatics built in. It's carrying the information. You can reconstruct potentials far away and their long range effects. So when you have cumulative effects through a material, using the density as the descriptor is this almost perfect way of capturing that. And people are sort of rediscovering this even as they learn these machine learned potentials, atomic potentials. They're now beginning to build in some of these density effects in order to get the long range electrostatics right. And so the density really captures, is this sort of fantastic descriptor for sort of recreating a local environment, but carrying information from far away, right? The long range sort of charge and dipole and quadrupole information. Does that help?
Yeah. Thanks for that, and good to see you again.
Good to see you.
We got a question from John Ferrier here, a student in the audience. John?
Hello. My question is going to be a lot simpler than those ones. I was basically, given where the people worked on this, assuming that everything's done in Python with TensorFlow. Is that correct?
Well, I think, the earlier stuff, right, was sort of a little bit before TensorFlow was in good enough shape. So some is, and then some is still a bit homemade, right?
Okay.
And we're working all the time to get stuff onto iTensor and that to make it available. Yeah.
Okay, and with that in mind, do you have somewhere public where someone like me could go and read through the code and learn from it? It always seems to be a struggle when I read papers.
Right. So I'm not up to date with what fraction of things are available. Sort of everything that we had done was sort of homemade at the time that we did it. And then some fraction of it was made more publicly available. So I think everything, okay, so I know for, certainly if you're interested in the machine learning parts, that there's, it's up on GitHub, and then Google's thing, on Colab, there's notebooks, Python notebooks for doing the cone sham regularizer.
where do I find these at for the research? Just on your lab
I think-
website?
Well, it's either in the paper, the PhysRev letter from earlier this year, or the supplemental info. I think
Okay.
it directs you to the Colab notebook. Yeah, and so all that is there, right? But I don't know if that includes the DMRG parts, right? I suspect not. Yeah.
Okay, thank you. I just wanted to look through it.
Yes, sure.
So that last comment brings me to so if I understood correctly, in order to train this optimization, you need a couple of exact anchor points that guide you, right?
Yes.
So how would you scale up this calculation to much larger systems if you cannot obtain those anchor points accurately?
Right. So there's two things. So one is like, it's very nice that if we take a given system and with just two of these anchor points, we can get the entire curve.
Mm-hmm.
But then the question is, can we only get the curve for that system, right? Then that isn't that much help. So what we saw was that in simple cases, like going to this H2 setup, we didn't need to retrain at all. The functional that we had gave us a very accurate curve right from the get-go. So then the question is, does that mean any combinations of hydrogen atoms in a chain will be good for? And no, I don't think that's true. And we're exploring that at the moment. And then the other question is, of course, when we change what the species are. So there's two general areas that people explore with their machine learned interatomic potentials, not strongly correlated things, but for, doing MD simulations with millions of atoms. So one is, I call it sort of configuration space, where you have a very simple building block, maybe one or two elements. And so people do this, say, for tungsten material simulations. And you explore the configuration space. So you make surfaces, you make defects, you make all sorts of things to train it on, and then run it. And then you can, simulate a crack in a material simulation. And the other thing is configuration space, which people who care about drug discovery do all the time, where you take a dozen or so common elements, biological elements, the main group elements plus some metals maybe, and you try to find all the different ways they can chemically combine, and you explore all the possible molecules that they can make. So that's chemical space rather than configuration space. So by getting our stretched things right and getting maybe, many different configurations of hydrogen atoms right, that's the configuration space part. What the Ryo Nagayan originally did was he did three different molecules, and then tested on 148 totally different molecules. So that was chemical space. And they were all at equilibrium. So they're all weakly correlated. So we don't know yet how well this will generalize, but the initial indications were rather positive. What all of this points to is, well, it's great to get, for a simple system, the exact functional somewhere inside your neural network, right? Then the problem becomes, how do you get it out, right? So what features is the thing using in order to get these results? Can you condense it into a bunch of features that we would recognize, right? Like the local charges on the guys or whatever it is, right? And we didn't really do that, right? We didn't emphasize the fact that we didn't do that, but we didn't do that. but that's in some sense the next step, is to compress out the information, which part of what you're doing by just doing experiments to see when it generalizes and when it doesn't, right? You set it up and it can give you numbers for a given density, and so it gives you predictions, and so you just do it by testing, and then you begin to see, well, sort of what is it knows, right? And we can also, correlate it with features that we think are relevant to see if we can reproduce the same results using, not the density everywhere, but things that we think are important for getting strong correlation right.
Thank you.
Sure.
Adrian, can I jump in here, maybe?
Sure. Go ahead now.
Adrian. So as Adrian can tell you, Kieron, your colleague Steve White made his bones with Duncan's gap with a spin chain.
Yes.
Right?
Yes. Right.
And so you know the story very well. There's two phases for the spin one phase: the Heisenberg phase for antiferromagnet, and then the AKLT phase. The kind of well, I'm getting a little confused. The AKLT is same as Heisenberg, and then there's a boring phase where it kind of just dimerizes or kind of sits there. It's you can cut it and you don't get much entanglement. And I mean that's true also of the Haldane phase. But okay, let's not. Okay, let me try and say the question. So the question is, what about bosons? And yeah, and so I'm thinking simply, right? So when we think about this 1D model, right? And we don't do spin because we're simple men. And so there's spinless fermions moving in a 1D system on a lattice, right? Because DMRG to train the potential of that. So there's a famous mapping from Jordan and Wigner that maps spinless fermions in 1D onto what we call hardcore boson, or in other words, the spin 1/2. And what we call the potential is the Z component magnetic field that says, put a boson here. And what we call this exponentially decaying repulsion is just like a nearest neighbor or a third nearest neighbor repulsion.
Right.
And so then this question comes of, thinking about the strong correlation. It seems like the strong correlation limit is something to do with breaking bonds in chemistry, right? When you're sitting in a chemistry department, we want to break some bonds, make some new ones. And in the strong correlation picture is that you're going through some kind of phase transition, right? And so what used to be a highly excited state, and so Comchan has no right to get it right, now becomes the ground state. And at the crossing point, we get some avoided crossing, And so the thinking is maybe we can use the beta-ansatz kind of exact solution for spin chains, or something maybe simpler like the AKLT solution, to try and get out of this what would you call the weakly interacting ground state, the boring bound state, and to get thinking about chemistry like a cis-trans transition, right? So the trans, say for retinine, we had a talk last week about retinine. It's cis before the light. Then it sees the light in our eye and it becomes trans, let's say. And we think about these two molecules, the trans is an extremely excited state. It's separated by a visible gap, 500 nanometer gap from the ground state. But if you rotate the molecule, it suddenly becomes this metastable ground state that you can, that fluoresces at 580. So the question is somehow, what about bosons, and can we do better in finding this new ground state for a molecule, the one after the reaction?
Right. So I mean, there is DFT for bosons, right? You can apply exactly the same theorems. The equivalent of the Cohen-Sham system is less interesting since everybody can sit in the lowest state. And I've never worked with sort of boson systems, but I think what could be extremely fertile ground is seeing if one can sort of prove Holmberg-Cohn style theorems specifically for spin sort of chain problems. And because, so there's two things. One is, it turns out that these local approximations that people use in DFT are really large particle number approximations. There's a very specific limit in which the sort of particle number becomes large. The interaction becomes weak in the sense of between any pair of occupied orbitals, it's going to zero. But because there are n squared, roughly, pairs of occupied orbitals, the net effect is not going to zero. So it's a sort of semi-classical weak interaction limit. So that happens because it's a large particle number. Now, electrons have spin 1/2. So an awful lot of things to do with the spin, which I didn't emphasize at all, and a lot of magnetic properties don't necessarily come out so good with DFT, and that's because you're further from that limit. Whereas if you take spin lattice models and you play with the actual size of the spin, right, you could check to see if certain simplifications occur for large, when the spin number gets large. And still sticking with fermions. But people haven't done much of this. And part of the reason there's very little in the literature is because people who look at these spin chains tend to look at the homogeneous case only. You tend to have the same on-site potential or periodic, at most a sort of periodic thing, but it's homogeneous, right? It repeats. Whereas to understand anything in terms of these density functionals, the crucial part is that you must make it inhomogeneous in order to see what happens and how things change. I mean, that's how the whole theory works, is this one-to-one correspondence. And I don't think much has been done to prove these kind of one-to-one correspondences for the systems, because a lot of the, so when we did these sort of review articles basically on, two-side Hubbard things, there was lots of stuff in the literature that have been going on since the maybe 80s, many body people looking at things. But in most of it, almost all of it, was always in the symmetric case. And you can't see any of the functional dependence if you keep it symmetric, right? And if you think of, one-dimensional Hubbard chain, right, of any paper you've ever seen where that's been there, I bet it was, the same site everywhere, right? Except for the odd DFT paper somewhere. But other than that, right?
In the spirit of your response to the question about your own paper, so there is one paper that does talk about the homogeneous case that comes to mind. It's one of my own, and what we consider is the case of strong inhomogeneity. It's an idea that goes back to the early 80s, thinking about silicon with dilute phosphorus. It's the original kind of Mott disordered insulator. When you go to the limit of these hydrogenic shallow impurities that are far apart, it kind of gets to that bond broken regime, right? But the distribution of couplings is strongly inhomogeneous. It's a Poissonian distribution where you're going to land, and you get an exponential tail. So you fold an exponential and you get these long tails to the coupling strengths. And we do it in 1D, as you do. And in 1D, there's an asymptotically exact description, I think first worked out by one of the Fisher boys in the late 80s, that gives you some control of the inhomogeneity and allows you to describe the fixed points and see how it transitions. Coming back to the boson case, thinking about 3D, Bohm, David Bohm and David Pines. One of the Pines, maybe Alex Pines or David Pines, I get them mixed up. The one who founded Aston, that Pines. They have this Bohm-Pines approach to the intuition that you were expressing a moment ago about why it's good to use the density. And they do it in the language of what we call the random phase approximation. It's a phrase from Gell-Mann's calculation from the 40s or whatever. But in principle, what it has to do with is you put in a boson, and they call it the plasma resonance or whatever, and it takes care of the Q equals 0 pole that the lattice is supposed to take care of for you. They call it jelly, you know, because they put in some background screening potential that has no, it's homogeneous, right? That's what you're talking about. And that plasmon part, when they, you know, in their random phase approximation, it's equivalent to the bubble and all that, it screens down and leaves you with fermions that are local in their interactions. So maybe they have a hardcore U when they're on the same site. We don't have to worry about that Q goes to zero singularity. And thinking in those in terms of what about both, this is a fancier question, the previous one. I would argue that this 1D stuff you're doing with Steve, it's already a spin chain within homogeneity. So you guys are already doing it.
Yeah, I mean, technically it is, right? But practically the stuff that we read off from it. No, because of the way, you know, you have these 20, so this is like an extremely multi-band Hubbard model, right? If you want to think about it that way. But because it's so extreme, right? We're looking at this other limit, which, you know, I mean, you can actually, if you peer at it very, very closely, you can see some of these one-dimensional physics things. But everything sort of, when you just plot it on a gross scale, looks like just like it does in 3 dimensions. So yes, technically it's the same, but practically it allows us to do these experiments that we have.
So really in 3D, how can we put in the plasmon? You know, when we're learning, right now we're trying to learn this density, you know, and using this cone sham, using this single slated determinant, you know. When we look at this random phase approximation paper, they kind of put an exponential factor in front. It has the flavor of that factor that Feynman and Fellows put in front for helium to take care of the conservation of flow. You put in like a dipole term and then do a variational calculation to try and make the superfluid helium have long range properties that are conserving approximation. So it feels like there might be a similar kind of trick inspired by this intuition that the density is the thing, that we could learn a wave function that has a plasma resonance to take care of the long range stuff. And then on top of that, these local interacting short range hopping fermions.
Well, the whole trick is to avoid ever needing to calculate the wave function, right?
Right.
And so, I mean, it's a logical trick rather than let's say, I mean, it's motivated by physical intuition, and the approximations capture the physics, as it were, but it's ultimately a sort of logical trick, right? You simply define this cone sham scheme, but it gives you this wonderful starting point, but should never be over-interpreted, right? The crucial thing about these theorems is if you stare at them long and hard enough, you can figure out what a calculation is supposed to be able to predict and what it isn't. And exactly as Bernardo brought up, right? The pure cone sham, the original cone sham scheme produces a gap, and people have shown, as we have done, that the approximations give you a good approximation to the cone sham gap, the exact cone sham gap, but they are not good approximations to the true gap. However, then you learn several decades later, right, that you can do these generalized cone sham calculations and extract good gaps from them. But you have to know the difference in the sort of these logical approaches to be able to discriminate between these two things. Everything you say about plasmons and things like that in the DFT context all has to be poured into and wrapped up in an exchange correlation function. And all it's doing is figuring out the effects of that physics on the ground state energy, nothing else. I mean, at least at a formal level, right?
The wave function has a phase. You know, like the wave function, when you square it, you get the density, but it has a phase, right? And that gets in the cone-sham theorem, when you look at it, you make the assumption you have a non-degenerate ground state. Is one way of saying it, right? But if you think about putting
no, the Holmberg cone, the Levy and Lieb generalized the Holmberg cone theorem to degenerate ground states.
Take the original one. Yeah, the original one. So now
the original simply assumed it, you know, in order to do the proof that way, and it turned out to be straightforward to generalize to degenerate case.
So the straightforward question is, if you put a metal on a loop, you know, say lead, right, and cool it down, it superconducts at 4 Kelvin of mercury, right? And in the superconductor, the phase matters. You got 2 degenerate ground states that differ by the flux through the hole. You can thread an HC/2 flux quantum through the hole. When you look at the successes for the sulfide, the hydrogen compounds, the sulfide compounds, it's the usual BCS business, where you first do the band structure and then you do the phonons, right? It seems like if we wanted to do a superconductor that would be like a real room temperature, you know, room pressure superconductor, we have to get to that approximation where get to that point where the Born-Oppenheimer is breaking down, where we don't have a weakly correlated electron, weakly coupled to phonons, you know, and the gap set by the Debye frequency. And, you know, you have to squeeze it to get a high Debye frequency or use hydrogen. That what we would need is something that cares about the phase of the wave function, and that goes directly to find the superconducting wave function, right?
And there is such a generalization of electronic DFT that was created by Hardy-Gross and Cohn about 30 years ago, in which you couple directly to the order parameter. So, and you couple the electrons and the phonons, and you have a coupling to the order parameter, and you use that as a field. So even though, you know, you might, you know, it can you know, you end up with Ely-Ashburg type equations just the same, except they are formally exact and there's a missing functional. And they've shown, Hardy, Gross, and many collaborators have shown over the last 10 years that you can use it to accurately predict superconducting temperatures of BCS type superconductors very well. I think including some of the more recent ones, the high pressure ones. And they've also tried it for the cuprates. The trouble is that you need to know what the mechanism is in order to design the functional approximation to capture it. So they have not been able to do that because, you know, difficulties in figuring that out. But there is, you know, so there is a working DFT of at least BCS type superconductivity, which gives you quantitative predictions for TC, for the superconducting temperature, that do not involve any empirical parameters. So there's no mu star or anything like that in them. So that does exist, but you know, the form of the functional will change depending on what the nature of the superconductivity is. Not surprisingly.
All right, we need to wrap up. So we're going to thank, the participants and Kieron for a very stimulating discussion and a very nice talk. We thank you all for being here today, and we'll see you next week. Thank you, Kieron.
Okay, thank you, Adrian.